we will introduce dot product and its properties. Suppose vectors v and w are in component form. Vector v equals v sub 1, v sub 2, and vector w equals w sub 1, w sub 2. v sub 1, v sub 2, w sub 1, w sub 2 are all real numbers. Then the dot product of vectors v and w are defined as vector v dot vector w equals v sub 1, v sub 2 dot w sub 1, w sub 2 equals v sub 1, w sub 1 plus v sub 2, w sub 2. Dot products are commutative. Vector v dot vector w by definition equals v sub 1, w sub 1 plus v sub 2, w sub 2. These letters with subscripts are real numbers, and they are commutative. W sub 1, v sub 1 plus w sub 2, v sub 2. How real numbers are commutative? For example, 2 times 3 equals 3 times 2. Of course, the result is 6. Then it equals w sub 1, w sub 2 dot v sub 1, v sub 2. We get this line by going backwards using the definition of dot product. It is the same as vector w dot vector v. Dot products are also distributive. We will introduce one more vector. Suppose vector u is in component form and both u sub 1 and u sub 2 are real numbers. Then vector u dot vector v plus vector w equals u sub 1, u sub 2 dot v sub 1 plus w sub 1, v sub 2 plus w sub 2. Using the definition of dot product, we have u sub 1 times the sum of v sub 1 and w sub 1 plus u sub 2 times the sum of v sub 2 and w sub 2. Remember, these letters with subscripts are real numbers, and we can use the distributive property of the real number to distribute the u sub 1 and u sub 2 correspondingly. It equals u sub 1 v sub 1 plus u sub 1 w sub 1 plus u sub 2 v sub 2 plus u sub 2 w sub 2. We will rearrange the terms to get u sub 1 v sub 1 plus u sub 2 v sub 2 plus u sub 1 w sub 1 plus u sub 2 w sub 2. Using the definition of dot product and go backwards, we have u sub 1 u sub 2 dot v sub 1 v sub 2 plus u sub 1 u sub 2 dot w sub 1 w sub 2. That's the same as vector u dot vector v plus vector u dot vector w. We will show part of the scalar property of dot products. We will show k times vector v dot vector w equals vector v dot k times vector w. The left hand side equals k times vector v dot vector w. By definition, it equals k times v sub 1 v sub 2 dot w sub 1 w sub 2 equals, using the definition of dot product again, equals k times v sub 1 w sub 1 plus v sub 2 w sub 2. Remember that k and the other letters with subscripts are real numbers. We can just use the distributive property of real numbers. It equals k times v sub 1 w sub 1 plus k times v sub 2 w sub 2. We can rearrange the factors of each term to get v sub 1 times k times w sub 1 plus v sub 2 times k times w sub 2. Using the definition of dot product and go backwards, it equals v sub 1 v sub 2 dot k times w sub 1 k times w sub 2. It equals v sub 1 v sub 2 dot, we can pull out the factor k to get k times w sub 1 w sub 2. That is the same as vector v dot k times vector w is equals to right hand side. Now we can establish the other properties of dot products. Number 1, k times vector v dot vector w equals k times vector v dot vector w equals vector v dot k times vector w. Number 2, vector v dot itself equals v sub 1 v sub 2 dot v sub 1 v sub 2. By definition of dot product, we get v sub 1 squared plus v sub 2 squared, which is the same as the square of the square root of v sub 1 squared plus v sub 2 squared. That's the same as the magnitude of vector v all squared.